Welcome you all for today's NPTEL online course on smart grid, and today's lecture will be discussing on simulation and case study of DC microgrid. In our previous lecture we have focused on simulation and analysis of AC microgrid, and we have seen that AC microgrid operated into different mode of operation, both grid connected and isolated. We have chosen 7 different cases that may commonly appear in a day to day life, and those cases have been analyzed in the presence of distributed energy resources, and we allowed the load to change from one magnitude to the other, and the simulation results have been presented briefly. Today we will focus on DC microgrid. About DC microgrid, one thing is very interesting. We have seen the merits of DC microgrid and the importance of going for DC microgrid just to avoid multiple conversion levels, that is from AC DC AC or DC AC AC. So, to avoid multiple conversions, we prefer to go for DC microgrid, but being said that DC microgrid can be connected along with grid or operate along with the grid, or it can also operate with autonomous or isolated mode of operation. But commonly DC grids in an isolated mode become very popular because it is easily achievable, and when you have a grid, most probably we may not prefer to have a DC grid. We can have a hybrid AC DC grid, but only DC grid having a grid AC grid in place may not be very commonly seen today. So, in this lecture today we will focus on DC grid simulation and analysis when it is operated in an isolated mode. That means an independent grid catered with a DC bus or a DC voltage, but it may so happen we may have multiple DC grids and they may exchange or support each other, complement each other or communicate each other for a better operation of multiple DC grids. So, today's lecture is mainly focused on simulation and analysis of a single DC grid, or it could be multiple microgrids. Multiple microgrid simulation in the platform of DC or an independent DC microgrid simulation can be analyzed. Moving to isolated DC microgrid operation, there are two major operational issues. One is case 1, where standalone DC microgrid system, which is very common, feasible, adaptable and realizable. Now, moving to case study 2, where interconnection of two local DC grids means in a remote there are two remote villages, they both have actually DC microgrid in place, but they like to operate together because they do not have any grid support at all. Now, standalone DC microgrid, this we have already seen. This is a structure of my DC microgrid where we have PV panels, and we can see that we have PV panels and we do have actually diesel generators, battery, supercapacitor and also perhaps wind connected to my system by AC DC 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 conversions, and we have 3 different type of loads where some of them are very critical and some of them could be non-critical. So, this is the basic architecture of DC microgrid is being considered for further analysis. The system description: system consisting of renewable energy sources, that is could be PV or wind, hybrid storage systems, that is combination of battery and supercapacitor, non-renewable energy sources such as diesel generator. If you like to electrify a rural remote area through DC grid, we can certainly encourage the presence of PV as well as wind along with battery and supercapacitor in place Further, we can have a diesel generator looking into evening hours load catering. If the renewable energy source is not enough to meet my load, then certainly the diesel generator can come to active participation. 3 loads are considered in the simulation, where 2 of them are considered to be non-critical and one of them considered to be critical. Means under no circumstances one load can be taken out or compromised, whereas 2 non-critical loads can be compromised if my renewable energy sources and diesel generator is not able to meet those. Now, PV is connected through the boost converter to isolated DC microgrid. Output of the wind turbine is processed through DC-AC, DC-DC conversion to feed power. Battery and supercapacitors are connected to isolated DC microgrid through bidirectional back boost converter for bidirectional power flow, because they can be charged or they can be discharged. Diesel generator is interfaced to my isolated DC microgrid through the controlled rectifier. Now, this is one of the control algorithm which has been developed for DC microgrid system. Now, let us go carefully step by step. Now, let us say my load which is PL and the generation which is PG. Now, the generation may be more than my load, or sometime the P generation may be less than my P load. So, how do I optimally utilize my resources available to me to operate my DC microgrid when my generation is more than PL or the load, or when my generation is less than PL? Certainly, we need to store when the generation is excess and you have to discharge your battery when the generation is minimum. But let us and depending upon the state of charge conditions of the battery. Now, if the P generation is greater than PL, if it is true, that means, and if the battery is at SOC which is 90%, and if it is not charged up to 90%, then I can charge my battery and allow my PV and wind to operate at its MPP. Concentrate. If the generation is more than load, I do have excess energy. Check whether my battery has been charged up to 90% or not. If it has not been charged up to 90%, and if my generation is more, then I can allow my battery to charge as well as keep on generating. Do not reduce the generation from PV or wind, allow them to operate at a MPPT mode. Now, if it has already been charged up to 90%, then PV and wind bus will go to regulation mode and the battery will be ideal. We will not charge further. But if P generation is not greater than PL, means if the P generation is less, means you will follow this step. Check whether the battery which has been having the SOC less than 40%, if it is not discharged below 40%, then the battery can discharge to meet my shortage of generation and allow my PV and wind to operate at MPP certainly. But if it has already been discharged below 40, then I have no option, my generation is low and my battery which has already been discharged below 40. So, the third option available to me could be check with the available of diesel generator, and if the diesel generator is available to me, then the PDG can meet my difference between load and generation. So, whatever the gap between load and generation can be taken out from my diesel generator. Now, if it is excess, diesel generator is still excess, then I can allow my battery to charge, and if not, then I will come further to this point. Now, here I will see to that if the battery which is the state of charge is less than 30%, then I will charge my if it is less than 30%, then I will go whether it is less than 20%, and if it is yes, then I can go for battery discharging and single critical load can be met. I do repeat, if my diesel generator has having excess energy which is more than the difference between the load and the generation, then if it is greater, then I can charge my battery. If it is not greater, then I have to take some energy, because the diesel generator is not able to meet my load generation difference. So, that case I have to see whether my SOC state of the battery, and if it is less than 30%, so then it is not a good state to discharge. So, then if it is SOC is less than, if it is not less than 30%, then I can discharge. Critical load and non-critical loads are in operation, but if it is less than 20% and if it is not less than 20%, then I can go to one non-critical and one critical load and battery can discharge, but if it is less than 20%, then I will only switch on my critical load and start discharging my battery. So, please understand the algorithm is such where we try to understand what is the situation of the system. If my generation is more than load, then I can start charging my storage, but if it is less, but before charging the battery, if the generation is more, I have to see the state of my battery. If the state of battery which is fully charged, then certainly I have to make my battery ideal and do not operate my PV or wind at its MPPT. But if the P generation is more than PL load and the battery which has not been fully charged, then certainly I can charge it. But if the PG is less than my load, then what is the option? I have to check whether the SOC of the battery. If the SOC of the battery is not less than 40%, then I can certainly discharge my battery to meet my load. But it is already 40% less, then I cannot take my shortage of energy from my battery. So, I have to switch on my diesel generator. Now, once the diesel generator is on, if the diesel generator is able to meet the gap, then the excess diesel generator energy available to me can be used for battery charging. But if it is not so, then I have to see to the state of charge my battery. I have to keep on discharging to meet my loads, and slowly, because the battery is getting discharged, the diesel generator is not having the excess energy to meet the difference. So, that case I have to curtail my loads. So, first of all I have to curtail one non-critical load and then the second non-critical load, and the critical load can never be curtailed. So, that case from 40% to 30%, even up to 20%, even slightly below 20%, I can discharge my battery to protect my critical load. Now, the standalone DC microgrid system, where the main control system being adopted, where you see it is at MPPT operation, and this basic structure represent the control algorithm for the control scheme for standalone DC microgrid. Now, in case of a standalone system, now let us focus on a very interesting simulation where the first characteristic represent your renewable power generation and the second one represent your DC bus voltage, and this is the state of charge of my battery, and this is the power of my battery and supercapacitor. Then this is the load power, how the load is being taken care, and this is my diesel generator output. Now, we can see the power, renewable power generation, which is keep on varying over a period of time, and the voltage which is almost steady excluding few transients. And very interestingly, we can see that the state of charge of battery, which is keep on varying from 80% to 90 to 80 and then 40 etc. And then finally, we can say the characteristic of battery and supercapacitor, the power, and this is how the load is keep on changing, and the diesel generator characteristic. Now, one very interesting thing I like to tell you here, when the state of charge of the battery is at low, we can clearly see the diesel generator is operating with its maximum capacity, because certainly it is active, because the battery is not able to meet the load, and if this characteristic has been zoomed to this picture, where we can see how my supercapacitor and battery they behave during transients. And this is one more characteristic where the power is varying and the voltages, the SOC of the battery and supercapacitor power characteristic, load power, and my diesel generator. So, in one case the diesel generator is not at all active, because it is not required for my diesel generator to be switched on, whereas in the other case at 14th second the diesel generator came to action. Perhaps because the load is slightly low, we can see the load is at 2, and here the load is reduced, whereas the load is reduced. So, one scenario where the load is reduced. So, you can see this is a scenario where the load is at 3 and the generation is at 1. We have seen another case where the load is at 3 and the generation is at 3.5. So, one case where P generation is greater than P load we have simulated, and the other case where P generation is less than PL. So, it is certainly clear when your generation is more than load, then the diesel generator may not be brought into the system operational conditions, whereas the generation is less from the renewables, the DG come to play. But the characteristics depends on how your battery status and how they have been designed. So, we can clearly see only when the battery falls below a particular SOC, then the DG come to active operation. Now, we will consider the isolated mode of DC microgrid, but instead of one DC microgrid, now we will concentrate on 2 DC microgrids and interconnection of these 2 local DC microgrids. The first of all, why do we need to have integration or interconnection or complementation between 2 DC microgrids? Now, this is how we have a DC microgrid 1 of a village 1, let us say, and this is another DC microgrid of another rural area or remote area, and these 2 have been connected to a DC-DC converter. But one thing is very clear, both the DC microgrids are not necessarily operating at the same voltage level. One is operating at, let us say, 48 volts and the other may operate at 380 volts. So, the important challenge here, when you have 2 DC microgrids operating at different voltages, can they be interconnected and can they complement to each other? That is what the important analysis we like to focus here. What are the impact on the present energy system when you have integrated more than one DC microgrid, or more than one DC microgrid are being operated together? The energy security will increase. For example, one DC microgrid do have condition where the generation is more than load, and we have seen the other case where the generation is less than load. Now, when the generation is less than load, we have seen the diesel generator has to be brought actively once my battery not able to meet the load increase. Now, if you have 2 systems, in one case you have excess energy and the other case you have shortage of energy. Now, instead of bringing the DG in the other system where the generation is less from renewables, perhaps I can take the excess renewable energy available in the other microgrid to meet my energy shortage in the other microgrid. So, perhaps it is one of the wonderful opportunity for the DC microgrids to operate in cooperation and complement or support to each other. First of all, we can achieve local energy security, effective renewable energy sources utilization, reduction in cost, high reliability, eco-friendly generation and supply quality improvement can be achieved. Now, this is how actually the structure. So, we have this is DC microgrid 1 and this is my DC microgrid 2 and they two are interconnected System consisting of two autonomous DC microgrid spatially apart from each other with considerable line resistance between them, means we have two DC microgrids separated reasonable cable length between these two. Each DC microgrid consists of one photovoltaic source, battery as equivalent to group of source from renewable sources and storage devices etc. PV sources is interfaced to DC bus through boost converter and bidirectional buck boost DC-DC converter is utilized for connecting the battery storage. Interconnection of two DC microgrids is realized by considering DABC as interfacing unit which provides galvanic isolation and high power feeding capability in both direction along with large conversion ratio through high frequency transformers. Two full H bridge converters are connected to either side of the transformer to produce the high frequency AC from DC. Now, this is the proposed power control management strategy between autonomous DC microgrids. We proposed the communication independent control. It enhances the system reliability and efficient utilization of resources, covers the over and underloading of autonomous DC microgrids. It includes overcharging and under discharging of storages. Now, we can see this strategy region 1 where the autonomous DC microgrid 1 is feeding energy to autonomous DC microgrid 2 and the region 2 is being used when the autonomous DC microgrid 2 is feeding energy to my autonomous DC microgrid 1. Now, this is control loop of the battery of my autonomous DC microgrid 1. We can see MPPT operation, we have controller and finally two PV converters. So, this is this control strategy for my PV and we can have this control strategy for my battery. Now, moving to control loops of DC microgrid, basic structure and then we have a load shedding control, because here we have seen that if required the loads which are not critical that need to be shed or disconnected. Now, there are two microgrids have been considered here and we will see the rating those have been considered before simulation. First of all, let us consider the autonomous DC microgrid 1 where we consider the PV capacity of 4.5 kilowatt, then the battery which is of capacity 200 ampere hour and the nominal voltage which is at 96 volt for these two, and very importantly the nominal grid voltage considered to be 380 for my DC microgrid 1 and voltage thresholds have been assumed and the fixed load which is 1 kilowatt which cannot be varied and we have a variable load of T kilowatt. So, 1 kilowatt of fixed load and 2 kilowatt of variable load. Now, moving to autonomous DC microgrid 2 where the PV capacity which is of 750 watt, the battery which is of 100 ampere hour operating nominal voltage at 24 volts and the rated nominal grid voltage assumed to be 48. So, we do have 3 one autonomous DC microgrid 1 operated 380 volt, autonomous DC microgrid 2 operated 48 volts, and the DC loads which is 200 watt fixed and 300 watt variable. So, indirectly we do have a larger system operating at large voltage rating, that is 380 volts. We have a very small microgrid, DC microgrid operate at low voltage at 48. So, now we want to interconnect these two. Now, when we focus on autonomous DC microgrid control, it is mainly effective management of source and storage based on bus signaling method. It has distributed control. Very importantly, it eliminates the communication between the buses, embrace the extreme scenario of individual DC grids, enclose the constant power loads, bus voltage deviation are within allowable range. Now, this is my operation of my autonomous DC microgrid 1 and this is my autonomous DC microgrid 2, operate at 48 volts and operate at 380 volts. We can clearly see this is my bus voltage which is very close to 380 and this is very close to 48 volts, and we can also see the irradiation which is varying, and in case of microgrid 2 it is also varying, whereas the PV power output which is more or less close to 2 per unit, and here it is close to 350 or 325 watts. Now, then moving to battery terminal voltage which is varying, we could see the similar scenarios. Then battery output power, and then with this is my load power which is varying from 2 and goes up to 2.5, and here it is varying from 350 to close to 400. So, as you have seen, in case of my microgrid 1 the load is close to 3 kilowatt. So, this is what it is, very close to 3, and this is at 400 or 300 watts. So, it is operating very close to 300 watts. Now, inter DC grid power flow, two practical DC grid voltages, one is at 380 volts and the other is at 48 volt are considered. Effective control and coordination is achieved without communication based on BSM. Proposed control strategy is found and stable even under wide power variation. Comparison of proposed scheme, and it has been seen that the communication which is not required, control complexity is very low, isolation provided, voltage trace of the BDC is very low, reliability is extremely high, and the power sharing between DC microgrid is flexible, means excess power can brought from DC microgrid 2 to 1, and we can also exchange power from microgrid 1 to microgrid 2. So, here now we are putting both the DC microgrids simultaneously. Now, we can clearly see that this is showing the voltage of my microgrid 1 which is around 380, but it is varying, and this is for my microgrid 2 which is around 48, and then we can see that the power exported from my microgrid 1, there is almost slightly exported, and you can say this fellow is observing the microgrid 2, and when he is importing, now the microgrid 2 is exporting. So, we can see this is kind of a mirror image, as and when there is, they both are operating at 0, suddenly if there is a requirement, then the DC microgrid 2 is receiving power and excess from the microgrid 1, and when it is excess for microgrid 2 being observed by microgrid 1. And finally, we can say power within the microgrid 1 as well as power within the microgrid 2. We can see the load characteristic, we can see the PV characteristic and we can see the battery characteristics. So, we can see within the microgrids the power output of the battery, load and the PV can be seen, as well as there is a power exchange between these two grids are possible without violating much of the voltage requirements at 380 and 48 volts. So, this is an extremely challenging task, and if it can be achievable, then the system reliability will certainly go up, because you need not bring your diesel generator unwantedly if there is excess power available to you the nearest DC microgrid. And all the presentation are mainly out of these two IEEE transactions as well as one general meeting article. And with this we like to conclude that the DC microgrid is an important task. Simulation is achievable, but very importantly it has been focused here how the DC microgrid in an isolated mode can operate, and we also extended this analysis to a multiple microgrid operating at two different voltages and capable of exchanging their power to benefit each other. Thank you very much.